It would be better if everybody could hear us on the recording. Okay, like I said, I'm probably about 90% of the way done with the exam. So far, everything's going well. I should have it back by Wednesday. One of the things that I'll mention now while it's on my mind. So I use, when I grade exams like this, I use what's called a correct for data approach. So what that means is that if I have an exam problem, and let's say that there's 10 steps, and you miss step 3, you're obviously going to have problems with the values in the remaining steps. But if the mistake is only on step 3, I'm only going to deduct points for step 3. I'm not going to say, oh, well, every step is wrong, right? Well, that's going to happen if you have one mistake and those values carry through. So, I mean, that's sort of the reason it takes so long is because, like, for example, on problem 2, I had situations where there was one positive that should have been a negative, and it made the whole answer wrong, but it was just one mistake, right? So it takes a little while to go through that. That's the big thing. So it's not to say there won't be a deduction for it, but your answer might be wildly different than the final answer just because of that one little sign difference. So, all right. Don't forget the career fair, which is on Wednesday from 12 to 4. So it starts right after this class. It goes on for 4 hours in the rec center. If you're interested, bring resumes. It's probably not a bad idea. Okay. Sound good? Everybody got the code? Okay. All right. I want to get into our topic today. And I'll preface this topic by sort of saying that I think that the lecture last time where we were doing this is necessary. I don't want to say it's not necessary because you can't compute a moment in 3D without this. But I'll admit that I think that the answers are a little abstract. You get this answer that's 4,000 times I and negative 30,000 times J and 20,000 times K, and you go, okay, what does this mean? And so there's kind of a separation from maybe trying to sink your teeth into it. Like what's the tangibility of the answer? And so I think that what we're going to be talking about today really will address that. And so what we're doing today is we're going to look at moments in 2D. In other words, what happens when we're restricting our forces and position vectors to 2 dimensions? What happens to the answer at the end? And then we're going to use that concept as a vehicle to really dig into what moments actually mean. So this is a really, really powerful lecture today. We are still going to use the formal definition of the moment. We're still going to be doing R cross F. So if you notice here on the board, I got a bunch of stuff written here. I'm going to reference this here in a bit. But keep in mind that the definition of a moment is still going to hold true in 2 dimensions, whether it's 2D or 3D, it's not going to matter. Remember, the definition is R cross F. R is a position vector, F is a force vector. And for that position vector, it starts at the point about which we're summing moments. Remember, moments are an action that increases a tendency to rotate. And so what we'll do is we'll select a point and we'll go, okay, what is the tendency to rotate about that point? And so we sum with the vernacular we use is we sum moments or take moments about that point. Okay? And so about some given point, we have a position vector that starts at that point and it ends anywhere along the line of action of that force. And we demonstrated that last time that if we have a point of interest, we could have 2 different position vectors, but as long as those position vectors point to that line of action, you'll get the same cross product. Notice that we can also determine the magnitude of the cross product or the magnitude of the moment by taking the magnitude of the force times this moment arm. The moment arm is the shortest distance from that line of action to the point in question. And we're going to do some stuff with that today. Okay. Like I said, today's lecture is going to be focused on moments in 2D. Why is that important? Well, for one, let's talk about reality. We as engineers are interested in solving problems. And when we solve problems, a lot of times what we try and do is make the problem as simple as possible, not as hard. Okay? Sometimes problems are difficult and we must deal with them in 3 dimensions. But if we can deal with them in 2 dimensions, we will. Take, for example, a bridge. A bridge is a 3-dimensional structure, but a lot of times we will idealize a 3-dimensional structure into a 2-dimensional model. Okay? And whether we're dealing with civil engineering applications or mechanical engineering applications or even biomedical engineering applications, a lot of times we will try and resolve those into 2D or even 1D problems if we can in order to make the analysis more straightforward. The simpler we can make our calculations, often the better in terms of safe and efficient designs. Okay? Now I want to talk about how that affects the math though. So let's look at what I have here on the board. And don't worry, what I have here on the board is on the next slide, so you're not going to miss anything. But what I have here is a definition for a position vector and a definition for a force vector. So if I want to determine a moment, r cross f, I get this, and then I can take this and write it in this fashion. Everybody okay with that? Now my question is, what if we're dealing in 2 dimensions, not 3? So maybe one way of dealing with that is maybe we'll take these terms, set them equal to 0. That would take this force vector and this position vector and restrict it to 2D, right? If we said there isn't a 3D term. So far so good? So how would that affect the answer? Okay, well, here's r cross f, so that means that that term would be 0 and that term would be 0. Okay, and so what would we have here? We would have this cross product. Okay, so let's see, that's a z term, that would be 0. That's a z term, that would be 0. That's a z term, that would be 0. And that's a z term, that would be 0, right? Okay? So, how would, let's carry this through. So, all right, so how would we evaluate each of these? So how do we do this determinant? What do we do? That times that minus that times that? What is that going to be? 0. There's not going to be any term here, right? What about over here? What do we get? This times this minus that times that? 0. This is the only thing that has a term, right? So, in fact, if we were to simplify this, we would say, what do we get? That times that minus that times that. So maybe Rx, Fy minus Ry, Fx all times the k vector. So, so basically what I'm saying is, if I had a moment in 2D, I now have just a simple formula that I can use to compute that moment, right? Notice how it doesn't matter what the force is. It doesn't matter what the position vector is. The resulting answer is always going to be along the z-axis. I mean, think about what's going on here. So here's a coordinate system. Right? If you have some point here and some force, right? The question is whether that generates moment that way or generates moment that way. But my thumb is either going to point out of the board or in the board, right? In other words, my thumb is only going to point towards the z direction, which is why in 2D, moments are only about the z-axis. In fact, a lot of times, because we're dealing in 2 dimensions a lot during our analysis, we don't even bother with the vector notation. In fact, really all we care about is just the magnitude. And the magnitude is just going to be that. Because of the nature of the problem, yes, it is a vector, but we know that vector is going to be along the z direction. Does that make sense? Now, one of the things I do want to point out, and don't worry, I'm going to highlight this in these slides here in a second, but I think it's kind of nice to have this a little tactile here in your notes. One of the things I want to point out is the right-hand rule. Now, how does the right-hand rule work? Okay, when we do r cross f, right, we take our fingers point towards vector 1, then we curl them towards vector 2, right? And then our thumb points in vector 3. Well, we can use that analogy to make a very simple observation. But let's just sort of take a step back before we get to that observation. what is the difference between a force and a moment, right? A force is an action that increases a tendency to translate. And a moment is an action on a body that increases its tendency to rotate, right? So if we're talking about rotation, right? And if we're talking about 2D, well, there's really only two ways something could rotate. It could rotate clockwise, or it could rotate counterclockwise, right? So which one's positive? Well, if I take my fingers, stick them towards the x-axis, curl them towards y, that's positive z. We can use that to make a pretty simple observation. That moments that are counterclockwise, we're going to take those as positive. And don't worry, we're going to elaborate on that here in a little bit. Okay? So what do I have here in this slide? This, right? So basically what I'm doing is I'm saying, okay, if we set this term here to 0, right, we get this, right? So that's 0, that's 0. This is the only thing with the term. And again, because of the nature of two-dimensional forces and position vectors, we often dispense with the vector notation or the IJK notation because it doesn't really matter. Okay? Now keep in mind, this is something else to keep in mind. This still holds too, that moments equal a force times a momentum. Okay? So far so good? Okay. So in order to illustrate this, I want to look at this example, and we're really gonna dig into this example. This is a really simple problem, but I really want to dig into this. Okay? Okay. I'll give everybody a sec to sort of jot this down. But I have here a pretty straightforward problem here. I have this lever here, which we'll call OA, and I have it, the lever, how long is the lever, by the way? It's 24 inches, and it's sort of at this angle, the 60-degree angle, and I have a 100-pound force applied at A. And what I'm going to do is I'm going to use this problem as a means of really sort of digging into what is going on with moments, okay? And so I'm going to determine the moment about point O. I'm going to do it a few different ways, or at least two different ways. And you'll see why here in a second, because I want to, well, really the reason why is I just want to illustrate that both definitions work. And then I'm going to ask you maybe what seem to be some really complicated questions, but they aren't. What would be the horizontal force at A that would generate the same moment? I apparently do not know how to spell, because that's supposed to be an L. W-O-U-L-D, not wound. So I'll fix that later. But what horizontal force at A would generate the same moment? And what is the smallest force that would generate the same moment? And so I really like this problem because it really illustrates a lot of what's going on here. Okay. Before we start doing some calculations, I just want to illustrate that the 100-pound force is a vertical force, okay? So I think it's worth noting the presence of that line, okay? And this line is the line of action of F, okay? That F acts in an up and down fashion. Okay? So far so good? All right. Sorry. Okay. So I propose that I have two definitions for this moment. Okay? The first is this Rx Fy minus Ry Fx. The second is Fd. Let's explore both of them, and let's see if we can determine the moment using both expressions. Okay, so okay. All right. Now, in order to compute the moment, I'm going to need a definition for my r vector and my f vector, right? Let's start off with the f vector because I think that's the easiest. Could somebody give me an ij description of my force vector?
0I plus 100j.
Okay.
Or minus 100j.
Yeah, I would say you're close. You're not right. It's minus 100j, right? Because the force is going down, right? So my force vector would be 0I minus 100j. And that is going to be measured in pounds. Would everybody agree with that, just from a vector description? Okay. All right. What about my position vector? Let's see if we can. Let's look at that. Okay. So I have this schematic right here. Okay. Now I propose that the position vector is going to look like this. Okay, where this is point 0 and this is point A, or at least this is one potential position vector, or at least what we're going to use for this problem. Why does this definition work? Because it starts at point O, right? It starts at point 0 because that's the point about which we're trying to sum moments, and it ends at a point along the line of action of the force. And this vertical line, that's the line of action of the force. Okay? So what I want is this term here, Rx, and this term Ry. Okay, that's what I want. Now, I do know a couple things. First off, what is this dimension right here? 24. That's 24 inches. And what's that angle? 60 degrees. Okay, so how would I compute Rx? Oh, there you go. Rx is going to be 24 cosine 60, and then Ry is going to be 24 sine 60. So So what are these? And by the way, let me go ahead and just put some notes up here, just so I don't have to. So what are we getting for Rx? 12 even, right? What about Ry? And we'll say like, I don't know, 2 decimal places. That's good enough. Sound good? So this is going to be, so what about our signs? Are they both, are they positive, negative? What's the deal? They're both positive because we're starting down here and we're going to the right and going up. So they're both positive. So this is going to be, what is that, 12I plus 20.78J. And what are the units? Inches, right? Okay. So far, so good? So if I wanted to use this vector description, I would say, okay, M naught is Rx Fy minus Ry Fx. Or in other words, the moment about point 0. Okay? So what are we going to have? Rx is 12 inches. Fy is 100 pounds minus 20.78 inches times 0 pounds. Sorry, say that again. Oh, yes, you're right. I'm sorry. Thank you. That's actually really important. Okay. So when we chug this out, what are we going to get? That term on the right is 0, so we're just going to get 12 times 100, right? Or 1200, or more specifically, negative 1200. Now, what are our units? This is sort of like a torque, right? So I'm going to say that our units are inch pounds. Sort of inches times pounds, as it were. That's going to be my units. Now, what is the deal with the negative? What does the negative even mean? Okay, well, let's go back to the very beginning of the problem. So here's the problem. Okay, now I want you to keep your eye fixed about point 0. That's our point O. That's our point of interest. Now, if I take 100 pounds and I stick it out here, which way is it wanting to rotate point O? Is it wanting to rotate it counterclockwise, or is it wanting to rotate it clockwise? Clockwise. Didn't we say counterclockwise rotations were positive? So this negative moment means it's a clockwise rotation. Make sense? So I propose that maybe a simpler way of describing this moment would be maybe like that. In other words, it is a 1,200 inch-pound moment. This is the magnitude. This is the direction. The direction is clockwise. Okay? Keep in mind, a moment is a vector. Okay? And what two quantities must vectors contain?
Magnitude and direction.
Magnitude and direction. And I propose that this is an apt description of a moment vector. We have a magnitude of 1,200 inch-pounds, and we have a direction. But the direction isn't that way or that way, because that would be appropriate for a force. A force is an action that increases a tendency to translate. So when we describe forces, we would say 200 pounds this way, or 400 pounds that way. Whereas with a moment, we're talking about 1,200 inch-pounds, and we're talking about the way that it would want to twist, or the way that it would want to rotate. In other words, a 1,200 inch-pound moment clockwise. Does that make sense? Everybody okay with that? Okay. All right. So far, so good. Okay. Now, I do want to consider an alternate definition of the moment about point 0 or point O. And that alternate definition would be to use this, just M equals FD. So I guess up here, maybe what I should do is say, up here we're using sort of the formal definition. Whereas down here we're using our alternate simplified definition. Now, let's see if we can reason this through, okay? Let's start off with F. F is just the magnitude of the force vector. And what is the magnitude of the force vector? It is 100 pounds, right? So far, so good? Okay. Now, this new term D, this is the first time I guess we've ever really dealt with D, is what I'm calling a moment arm. Okay? Now, what is the moment arm? It is the shortest distance from point O to the line of action of F. Okay? So let's draw a picture maybe. Oop. So this is point O. This is my force that has a magnitude of 100 pounds. And then that is the line of action. Now, tell me, let's go back to geometry. How do you define the shortest distance from a line to a point? What is the shortest distance from a line to a point? It's perpendicular from that line, right? Right? Like if you have a line out in space and you have some point, right? You could measure that distance, that distance, that distance, but the shortest distance is going to be perpendicular, right? Make sense? So what I'm interested in with my D value here is I'm interested in that distance. That's the shortest distance from that point to the line. And by the way, what is this distance? Rx in this problem. This is Rx. And what is Rx?
12 inches.
12 inches. So therefore, I could say this is just FD. It's just 100 times 12. The only, I guess, problem with this definition is that you must retain the context of the direction. But if I'm here and I have a point like this, it is going to rotate in a clockwise direction. Okay, now we're not done with this problem because I've got a couple of questions that I want to ask. And these questions might seem tricky, but they're really not, okay? But before I move on, does this make sense, these two definitions? Okay.
Is the 100 not negative in that scenario because it's magnitude?
That's a good question. So let's talk about that. I tend to not think of magnitudes as negative at all, okay? Because think about it this way. How would you compute a magnitude of an arbitrary vector? You use Pythagorean theorem, right? And what would the answer be from a Pythagorean theorem? You get a positive answer every time. You can't get a negative answer from that because you're taking the square root. So I think that the only way you can retain your direction is just through the context of the problem. So, make sense? That's a very fair question. Sound good? All right. Now, I asked 2 questions about this problem, and I'd like to explore these questions. Okay? Let's talk about question 1. What horizontal force applied at A would generate the same moment? Okay. All right, so let's wrap our head around this. Okay, so I'm a picture guy. Okay, so I'm going to draw some pictures. Okay, so here's point O, and what I am going to do is I'm going to replace this with a horizontal force at here, okay? Now I'm just curious, should this horizontal force, should it be going to the right or should it be going to the left? The left? To generate the same moment. Okay, so if I was pushing this way, which way would it rotate point O? Counterclockwise. So this force needs to be going to the right, doesn't it? In order to generate the same moment, I need to have a force going like that, right? And we'll say that the magnitude of this force is unknown. Okay. All right. Here's my line of action. Actually, good. There's point A. Now, which formula looks easier to deal with? This one or my alternate one? Alternate. Okay? So in this problem, let's use this formula a little bit. We know that this is going to be 1200, right? We know that this is an unknown. So maybe the big question is, what's that? So how do we do that? Well, maybe what we ought to do is remind ourselves, what is the moment arm? The moment arm is the shortest distance from this point to the line of action. And what is the shortest distance from that point to the line of action? Not Fy, but Ry, right? It's this distance. Okay? In this case, it's, so if, and then this is 1200, what's F going to be? How am I going to solve for F? And that's going to be about what? 50 something? 57. So bless you. So we'll call it something like that. Not too bad, right? not too difficult, is it? Not really. Not when you really think about it. It's pretty simple, you know. Like I said, I think this is the lecture where you really start to figure it out when it comes to moments. Let's see if we can ask this, figure out what's going on with this next question. What is the smallest What is the smallest force that you could apply to generate the same moment? Now, some of you might be thinking that when you hear the term smallest, that is analogous to the term minimum. And when you hear the term minimum, you might be thinking about a derivative, right? Because we'll take a derivative, set it equal to 0, find a minimum of a function, and all that. Not really necessary, okay? Because I propose that if you just apply a little bit of like basic common sense, you'll be able to figure this out really easily. All right, let me ask you a question, okay? Let's go up to the very beginning of the problem. Let's assume that this lever is a wrench, okay? And what you are trying to do is loosen the nut right here at O. How many of you, if you were doing this, would grab the wrench and pull it this way? How many of you would do that? Let me ask it another way. If I had that's the best I can do. If I had a bolt right here, and I had a wrench right there, and I wanted to turn that, what's the most effective way of applying the force right here? Maybe perpendicular? Do you see what I mean? I'm not going to apply it like that. I'm not going to get as much oomph, as it were, out of the action. Okay? So let's read the problem again. What is the smallest force that you could apply at A to generate the same moment? Let's diagram that. Maybe here's my lever. Here's point O, right? I'm trying to rotate O, what is it, clockwise? So maybe what I ought to do is apply a force like that, where that's the line of action. And so I am curious, in this context, what's my moment arm? 24 inches. Or, in this, you're exactly right, the magnitude of that vector, right? So in this case, what's F going to be? 50 pounds. What do you think? Yes?
Would you not need to give some kind of direction, like an IJ notation there?
That's a great question. That's a great question. if asked, you could do that, right? But, and we can talk about that, but an easy way of doing that would be just flipping your x and y terms on your position vector. I mean, think about it. How do you, if you're given a slope, and remember when you were graphing a line, how do you find the slope perpendicular? You just reciprocate, right? Same idea. So if you know that this angle is 60 degrees, you could find that angle pretty easily, right? Because I propose that this angle is just going to be 30. You know what I mean? So you could come up with it pretty easily. Does that make sense? But yeah, if you were trying to like more accurately describe the force vector, then yes. But the problem is asking what's the smallest force. It's just asking for the smallest magnitude. The answer is 50 pounds. But yeah, if you wanted to describe the direction, just 30 degrees down. Because, and where did I come up with that? That's 60, so just 90 degrees. What do you think? Not too hard, right? So this is, I think, where moments where it really starts to make sense, okay? So I thought this was it's a really, really valuable lecture. Okay, I've got a homework for you on that. I did want to sort of prepare you. Let me see. I think it's Wednesday. Yeah, it's Wednesday when we use a dot product. And it is our only lecture that we use a dot product. I'm going to foray into 3D like a little bit more. This, I will level with you. Geometrically, this is kind of a hard topic to work your head around, but it's probably the trickiest in the whole class. So after Wednesday, it gets a lot easier. So don't worry, we'll take our time with it. That's all I got, everybody. I'm going to pull the code up one more time, but I will see you all on Wednesday.